Welcome to Crashcast Java, the podcast where we dive deep into Java concepts and make them accessible to all. I'm your host Victor, and today we're joined by our resident Java expert Sheila. We'll be exploring an interesting concurrency technique called lock striping. Sheila, can you give our listeners a quick overview of what we'll be covering today?
Absolutely, Victor. Lock striping is a powerful technique used in Java to improve performance in concurrent applications. We'll start by explaining some fundamental concepts of concurrency, then dive into what lock striping is, how it works, and why it's useful. We'll also discuss its implementation, benefits, and potential drawbacks. By the end of this episode, our listeners will have a solid understanding of lock striping and how it fits into the broader landscape of Java concurrency.
That sounds great, Sheila. Let's start with the basics. Can you explain what concurrency means in the context of Java programming?
Of course, Victor. Concurrency in Java refers to the ability of a program to execute multiple tasks simultaneously. This is particularly important in modern applications that need to handle multiple user requests or process large amounts of data efficiently. However, when multiple threads access shared resources, we can run into issues like race conditions or data inconsistencies. That's where locks come in.
Interesting. So, locks are a way to manage access to shared resources in concurrent programs. But how does lock striping fit into this picture?
Great question, Victor. Lock striping is a technique that aims to improve the performance of concurrent applications by reducing lock contention. Instead of using a single lock for an entire data structure, lock striping divides the data into multiple segments, each with its own lock. This allows for more fine-grained locking and increased parallelism.
That sounds useful. Can you give us an analogy to help visualize how lock striping works?
Certainly. Imagine a supermarket with only one cashier. If there's a long line of customers, everyone has to wait for their turn, which is inefficient. Now, picture the same supermarket with multiple cashiers. Customers can be served simultaneously at different checkouts, significantly reducing wait times. Lock striping works similarly by allowing multiple threads to access different parts of a data structure concurrently, instead of waiting for a single lock.
That's a great analogy, Sheila. It really helps to picture how lock striping can improve performance. Can you tell us about a real-world implementation of lock striping in Java?
Absolutely. One of the most well-known implementations of lock striping in Java is the ConcurrentHashMap class. This class uses a technique called segmentation, which is essentially lock striping. The map is divided into multiple segments, each with its own lock. This allows multiple threads to write to different segments of the map simultaneously, greatly improving performance in highly concurrent scenarios.
That's fascinating. When was lock striping first introduced in Java, and is it still relevant today?
Lock striping, as implemented in ConcurrentHashMap, was introduced in Java 5 back in 2004. It was part of the Java util.concurrent package, which brought many improvements to Java's concurrency support. And yes, it's absolutely still relevant today. While there have been advancements in lock-free and wait-free algorithms, lock striping remains an important technique for managing concurrency in Java applications, especially when dealing with large shared data structures.
It's impressive that it has stood the test of time. Are there any common pitfalls or best practices that our listeners should be aware of when using lock striping?
Great point, Victor. One common pitfall is oversegmentation. While more segments can increase parallelism, it also increases memory overhead and can actually hurt performance if taken to extremes. A best practice is to choose the number of segments based on the expected level of concurrency in your application. Another important consideration is that lock striping is most effective when access to the data structure is evenly distributed. If most operations end up hitting the same segment, you might not see much benefit over a single lock. Lastly, it's crucial to remember that while lock striping can improve write performance, it doesn't eliminate the need for proper synchronization. You still need to ensure that your code is thread-safe.
Those are valuable insights, Sheila. As we wrap up, could you summarize the key points we've discussed about lock striping?
Certainly, Victor. To recap 1, lock striping is a concurrency technique that improves performance by dividing a data structure into multiple independently locked segments. 2, it allows for increased parallelism and reduced lock contention. 3, ConcurrentHashMap in Java is a prime example of lock striping implementation. 4. Lock striping was introduced in Java 5 and is still relevant today. 5. While powerful, it requires careful consideration of factors like the number of segments and access patterns to be effective.
Thank you, Sheila. That's a great summary. For our listeners who want to dive deeper, what are some advanced topics related to lock striping that they might want to explore?
For those looking to expand their knowledge, I'd recommend exploring these 3 areas. 1. Fine-grained locking techniques beyond lock striping. 2. Lock-free and wait-free algorithms for even higher concurrency. 3. The Java memory model, which underpins all concurrency in Java. These topics will give you a more comprehensive understanding of concurrency in Java.
Excellent suggestions, Sheila. That brings us to the end of today's episode on lock striping. We hope our listeners found this informative and engaging. If you enjoyed this episode, please subscribe to Crashcast Java for more deep dives into Java concepts. Thank you for listening, and we'll catch you in the next episode.